Moving on, we learn what is the value of the field with respect to the position R. We know that the field has to be smaller within the body with respect to outside, and we know that the mass of our field is larger where there is an higher density with respect to a lower density. Now we can impose a few constraints on our field, and this can be easily done because what we want at the center, for example, we don't want to have cusps. Okay, so we want that our field goes from lower values where the density is low, grows, reach a maximum at the center of the body, and then it goes down smoothly, and then again to a lower value outside the body. So we want something which is smooth. We don't want something like that, cuspy, like this case here. Okay, and that's the case whenever the derivative of phi of the potential, the derivative of the scalar field with respect to the radius is equal to 0. What does it mean, derivative equal to 0? That at 0, you see at r equal to 0, this is flat. Okay, we have something flat like that. We have a function smooth like that, no cusp in the center. That's given by this constraint here. Moreover, we want that our function describing the radial dependency of the field with respect to r at infinite give us phi of b. Okay, that's just because we have this expression at infinite. We want the value of the field related to the density of the background. So this is the other constraint. So these are the two constraints that we are going to impose to the radial distribution of phi of the scalar field. Then what we have to do is to find out what are the solutions for our field here, here, and in this transitional regime. To do that, the most convenient thing to do is to split this regime in three specific range. Okay, one is for the region A that goes from 0 to RA. One for the region B, which is outside the body, that goes from RB to infinite. And then we have the region C, which is in between. In doing that, we then start with the first region, region A, and we perform an approximation because we have seen that the effective potential looks like a bell like that. Okay, also here it looks kind of stretched, but here again there is the exponential. So we can around the 0, we can perform a Taylor expansion, keep only the first order, and it will look like this power of 2. Okay, so phi minus phi a to the power of 2. Just, you know, a parabola. That's just this is the first non-zero term in our Taylor expansion of the effective potential. Then, now that we have the effective potential, we can plug it in our Klein-Gordon equation. Remember that the Klein-Gordon equation that we were dealing with is this one. So I'm going to use this expression where the effective potential is given by our approximation. This one. Okay, therefore this is our Klein-Gordon equation. After we have linearized our expression, and the linearization takes place just by using this approximation, we have three solutions. So we look for the solution of phi for this expression, and one is going to be this one. So for phi equal to a constant, equal to phi a, you immediately see that phi equal to constant means that this guy is equal to 0. Phi a minus phi a is equal to 0. So you see this is a clear trivial solution. And then we have two solutions. So just perform double integral of this guy and you obtain this expression. So you see these are three solutions, 1 and 2 and 3. You see there is a plus and minus, so these are two different solutions. Of course, the general solution of this differential equation is given by the sum of these three solutions. So not the sum, the linear combination of these three solutions, and that's the expression. Then what we want you see that we might have a singularity here at r equal to 0. Therefore, to avoid any singularity, we can impose this condition that a1, so a minus, is equal to minus a plus. And this would avoid the singularity. If we do so, our expression becomes like that. Okay? And look that with this solution, that ranges from 0 to RA, this condition is automatically satisfied. So we are fine. We don't have any cusp in the core. That's good. Then we can look at region C. So we are looking for the intermediate range, this one in the middle. We do that. We are going to apply now an approximation. So you see, to have a full solution, I will go numerical. We cannot do it at the board or let's say here on paper. So what we're going to do is apply some approximation. We take our expression and we assume that this condition is satisfied, which is mostly the case for dark energy scenarios, okay, where this guy is typically in place. If we use this and this assumption, then our phi effective, the derivative with respect to phi of this shouldn't be a prime, this might be confusing, should be the derivative with respect to the phi, like that, okay, that's nice. Then we can have this guy is we can neglect this guy, so you see it disappears, and then we can use a Taylor expansion, this exponential for q phi much smaller than 1, which is equal to 1. So our Klein-Gordon equation for this regime can be approximated in this way. Then what we do, we solve this equation, which means we perform a first integration with respect to the radius, and then we integrate again, and we obtain the solution. So that's the solution for the region C that goes from RE to RB. Then we have the last interval, which is outside the body, therefore for R larger than RB. So we are looking for the behavior of phi outside the body. We have we are going to have again our Klein-Gordon equation. Again, this is a little bit misleading, so let me correct this prime, and this is going to be the derivative with respect to phi, okay, like that. Same approximation that we used before. Again, double integral of this guy, and that's what we obtain, okay, another simple solution. So we have split the entire solution that would tell us how phi would be from the center intermediate regime and into the outskirt into three different distinct patches. The three solutions are this one for the part inside the body, this one for the phi in the intermediate regime, and this one outside the body. Then you see that we have these constants A, C, D, E that have to be found by looking by imposing the border conditions. So this is what is done. So we just impose our conditions at R equal. Basically, you impose these three different functions that characterize the three intervals, such that they join smoothly where they touch each other. Okay. So let's say we have the solution for rho B and the solution for this part. Here, where they joint, we don't want to have any discontinuity, and we won't have to have a smooth function. And the same goes for this point where the solution here and the solution here are going to meet. Whenever we do that, we get this explicit form. Okay, so these are this very same expression 1, 2, and 3, 1, 2, and 3, with the constant A, C, D, E expressed explicitly. So for example, you see this, let's take, I don't know, this one, for example, that's the same for the other. You see it's a constant divided R plus C. The constant C turns out to be phi b. And just by looking for phi that goes to infinity, so you get this straight away. So our C is our phi b. And then the E is all this guy here. So this is a constant. This is a constant and it's equal to E. Okay, so these three expressions are these three ones here. Okay, for the three different patches that we considered.